Conservation of energy means that no energy can be created or destroyed. In a pendulum, this means that gravitational potential energy is converted to kinetic energy and then back again. In an ideal pendulum with no friction, total mechanical energy is conserved throughout, as potential energy is converted to kinetic energy in a constant exchange. When we first hang the pendulum up on the hook, we can see that the pendulum has zero potential energy and zero kinetic energy. But then when we lift the pendulum up, the energy that we put into the lifting action gets converted into gravitational potential energy. At the top of the pendulum here, the pendulum has maximum potential energy but has zero kinetic energy. When you release the pendulum and it swings down, the potential energy is converted into kinetic energy. At the bottom of the pendulum here, kinetic energy is at its max, whereas potential energy is at zero. But as the pendulum continues to swing up, the kinetic energy is converted back into potential energy, resulting in the potential energy returning to its max, whereas the kinetic energy returns to zero.
Okay, so the pendulum is going to be a phone that produces a frequency of 440 hertz. Now you might ask, why is the phone producing a frequency and why are we even harming our phone doing this experiment? Now the reason being is so that we can use the Doppler effect here. Now the Doppler effect is useful because Firefox has a very nifty feature that allows us to automatically get the frequency, the velocity of the pendulum as it swings. So using this, we have the phone that's swinging side to side, and to the observer, as the phone swings closer, the sound waves get smushed together and they start sticking, and because of that we get a higher frequency, a higher apparent frequency to the observer here. Now if the observer is on the other side, then the sound waves would instead spread out, creating a lower frequency. So as a result, you get an idea of the velocity. So this is how we are able to figure out the theoretical velocity and the actual velocity and see if the conservation of energy is a thing for the pendulum. And this.
Moving on to our method. In order to create a pendulum, we use the following: a meter stick with a hole at the top, duct tape, a nail, and two phones, one with Fifox tone generator and one with Fifox Doppler effect. At the end of the meter stick, we place the tone generator phone and secured it tightly with duct tape. Keep in mind to do these test swings after taping the phone in order to test its security before proceeding with this experiment. Once this is done, we then hang the apparatus on the nail, making sure to pad the space on the nail with duct tape to prevent it from wobbling as it swings. Then we had to mark the places on each of the angles we were testing. In order to do this, we use simple trigonometry. If the length of the meter stick is 100 centimeters, we can find the x value, or the horizontal length, using the length of the meter stick and the intended angle. For example, if we were testing 15 degrees, the 100 centimeters would be the hypotenuse side, while the x value would be the opposite. Thus, in our calculations, we can use sine 75 is equal to x over 100, with x being sine 75 times 100. Make sure to remember that 75 comes from 90 minus 15. Like that, we would be able to find the horizontal values and mark the values on the place we were gathering the data from. After this, we place the Doppler effect phone a certain distance away from the pendulum, taking special care not to put it directly underneath the pendulum in order to prevent any noise cancellation. From this, we can then swing the pendulum starting from the marked point and let it swing for a certain number of oscillations. In this experiment, we used 5. From there, we can extract the data.
The data was collected and processed using Excel and Desmos, including their inbuilt processes, such as average, stdev, and graphing. Based on the comparisons of the expected velocity to the data collected, the hypothesis wasn't entirely supported as the theoretical velocity for 15 degrees and 40 degrees are outside of the experimental standard deviation. 15 degrees has an experimental velocity of 0.90 meters per second, with a standard deviation of 6.70%, which lies above the theoretical velocity of 0.82 meters per second, while 40 degrees, which has an experimental velocity of 2.03 meters per second and a standard deviation of 2.82%, lies below the found theoretical velocity of 2.14 meters per second. This can be attributed to errors in the measurements, such as the assumption that air resistance could be treated as negligible in the calculations. As seen in the trials for 40 degrees, the pendulum spends more time swinging, causing it to experience more air resistance, which resulted in a lower experimental velocity compared to the expected theoretical velocity. Similarly, The trials for 15 degrees may have been faced with higher starting points, causing there to be a higher velocity than the expected value.
We can also use this experimental setup to understand the concept of isochronism. The theory of isochronism basically states that no matter which angle we let the pendulum go at, it will always oscillate with the same period at the end, and this is precisely why pendulum clocks are always in sync. So to do this, what we can do is instead of using Phi-Fox Doppler effect to match theoretical velocities to practical velocities, we can instead use Phi-Fox to time the oscillations as we let the pendulum go from different angles. We will notice that no matter which angle we let the pendulum go at, it will eventually lead to the same period where it takes for the oscillations to be completed, thus leading to the theory of isochronism.